Welcome to General Chemistry 2. We are going to pick up with the videos here in Chapter 10. Hopefully in your General Chemistry 1 class, you went through Chapter 9 in that class that you took. Obviously, if you took Gen Chem 1 with me, then you did go through Chapter 9. If you did not go through chapters 1 through 9 of the OpenStax book in your General Chemistry 1 class, I would highly encourage you to go to the Chem 1 video playlist that is on the same YouTube channel as where you're watching this right now, and go ahead and watch through the videos that I made for those chapters that you missed from Gen Chem 1. Because I'm going to assume that everyone that is in this class has gone through chapters 1 through 9 and is now ready to pick up where we left off in chapter 10, which is all about liquids, solids, and intermolecular forces. Mainly this last one here. The bulk of the chapter is over intermolecular forces. Before we get to that, though, just to kind of get the chemistry wheels rolling again, grease those gears that haven't turned in a while. Let's just talk about the three different phases of matter briefly here. And this will lead into intermolecular forces, but it's also a good way to just jump back into things. So if you remember, there are three common phases of matter here on planet Earth. There's a fourth phase as well, that is plasma, that we don't really pay too much attention to because there's not much of it here on Earth, although there's a whole bunch of it out there in the universe, namely stars are plasma. But like I said, there's not much here on Earth. We mainly have gas, liquid, and solid. And we're specifically going to be looking at water here, and its behavior and its properties in these three different phases. So in the gas phase, we would normally call this steam for water. Just as an example here, we're going to say that we have water at 100 degrees C in the gas phase. Water does not have to be 100 degrees or higher to be in the gas phase. And if you've ever walked outside in Oklahoma, in any of the months between March and November, then you know this to be true, because it is extremely humid here nearly all the time. And that water that is in the air that makes it a humid atmosphere is obviously not at 100 degrees C. So you don't have to have water at 100 degrees C for it to go into the gas phase. It just goes into the gas phase a whole lot easier if it's at 100 degrees C. And for our purposes here, we're going to just go ahead and say that we do have water at 100 degrees C. That sample of water in the gas phase has a density of about 5.9 times 10 to the negative 4 grams per mil. So pretty low density. It has a molar volume of 30.5 liters. You have to have 30.5 liters of this stuff to have a mole of it. And again, that's because gases, just naturally, the particles are very, very far away from each other. They're not interacting. They're just zipping around in open space until they smack into something and then they zip off in a different direction. That is how all gases behave. Liquid, on the other hand, liquid water at 20 degrees C, just as an example, has a density of essentially 1 gram per mil. For our purposes in labs, we always just assume 1 gram per mil. It's actually a little bit different than that, just depending on the temperature, but it's close enough that we can get away with it. That has a molar volume of about 18 mils. Much, much smaller. And again, it's because at the molecular level, these are much more closely packed. They're packed in a lot closer together than they are in the gas phase, where they're just zipping around willy-nilly. If we look at the solid phase, what we would expect to see is that that density increases again. So you can see here there's a big jump in density going from the density in the gas phase to the density in the liquid phase. There's a big jump there. and the molar volume, in accordance with that, has a big decrease. It gets a lot smaller. And so we would expect for that trend to continue, going from liquid to solid. And for most materials, that is true. Most materials out there, as you go from gas to liquid to solid, the density increases, and therefore the molar volume decreases. But not so with water. Water is different. If we look at solid water, which we would just call ice, the density of ice is actually significantly less than the density of water. Not like twice as, or like half the density or anything, but it's not like just a tiny fraction either. It's close to 10% less, the density of ice versus the density of liquid water. And you can see that reflected here in the molar volume. It has a larger molar volume than liquid water. This is why ice will float. As I'm sure you've had an ice water at some point in your life, the ice in that water did not sink to the bottom of the cup. Now, if you had a cup completely filled with ice, well then yes, there would be ice at the bottom. But if you only have enough ice to occupy a small portion of the cup, that ice is going to be at the top of the water because it is less dense than the liquid water. Hence, it floats. So that then begs the question, why the heck is solid water less dense than liquid water when nearly everything else is the opposite? Nearly everything else, as you go down, so to speak, in the phases, things become more dense because the particles become more closely packed together. But with liquid water versus solid water, it's the opposite. Solid water expands versus its liquid counterparts. And the answer to this, and so here Jean-Luc is wondering why water is behaving in such a strange way. The answer to this is intermolecular forces. The reason that water behaves in this strange way is because of the forces that are interacting between the different molecules. There are forces at work there that are not necessarily present or not nearly as strong with other molecules that we will look at later on. So, again, just to very briefly here go over the differences between those phases, and we've already covered some of these, but for gases, liquids, and solids, while they do usually have different densities, they're usually a lot closer to one another than they are to the gas. Gases are significantly lower in density than liquids or solids. A couple other things here that are things that we discussed in General Chemistry 1 as well, but you might remember we said that gases and liquids have indefinite shapes, so they take the shape of their container, while solids have a definite shape. Just depending on the type of solid, it could be something that you could maybe mold the shape, but once it's in a certain shape, it doesn't just move to form some new shape on its own. Whereas a liquid, if you're holding it in a can, that liquid will have a certain shape, and if you pour it into a glass, assuming that the glass is not the exact same shape as the can, it will have a different shape than it did before. Similar thing here with the volume. So liquids and solids have definite volumes. They don't expand and contract, just depending on the container that they're in, whereas a gas does. Gases have indefinite volumes. They just expand until they fill the container that they're in. One thing we're going to look at here as we go throughout the rest of this chapter is that another thing that is different from one phase to another is the relative strengths of the intermolecular forces. So gases tend to have relatively weak intermolecular forces, mainly just because all the particles are so far away from each other. They just don't have as much opportunity to interact with each other. Liquids tend to have moderate to strong intermolecular forces, and then solids have strong intermolecular forces, which is kind of required because if they're going to be a solid, especially if you're going to be a solid at a relatively warm temperature, you're going to need some really strong forces to hold that solid together to keep it from breaking apart. Alright, so if we're just going to again here compare gases and liquids, we kind of already talked about this a little bit, but liquids are not compressible. So if you try to take a liquid in a piston like this and you try to compress the liquid, you're just going to break whatever it is that you're trying to compress it with. If you stick a motor on that and try to use the motor to compress water, you're just going to break your motor. On the other hand, if you do that with gas, you can do that fairly easily, up to a point anyway. Gases are very compressible. You can compress gases very, well, relatively easy. If we look at solids, on the other hand, solids not very compressible, and there also tend to be two main categories of solids. You can have crystalline solids, and you can have amorphous solids. Crystalline solids are materials where you have a very regular, long-range order to the structure. There is a set structure, and if you look one place in the crystal, it is the same as everywhere else in the crystal, whereas in amorphous solid, there is no long-range order. So the arrangement of molecules in one area could be not dramatically different necessarily, but definitely could be different from one area to another. It's more like things are just kind of jumbled together versus having a very orderly structure. This is most easily seen, by the way, in plastics. Most of the time, if you have a plastic that is opaque, so light can't get through it, those are usually crystalline polymers. And the reason that it's opaque is because it's crystalline. So there's a solid crystalline structure that light has trouble getting through, whereas amorphous solids tend to be clear, like water bottles, for example. They're no less solid. They are just as solid as the crystalline solids, in terms of the definition anyway. They are just as solid, but because there's no long-term order, there's not as much for the light to interact with. There's no crystals for the light to interact with, and so while it might kind of warp the light, it might kind of bend it one way or the other, it's not going to completely absorb or block it like the crystalline solids would. And then, of course, here, to go from one phase to another, I think most people realize to go from solid to liquid to gas, you're just going to increase the heat. Or if you're going from liquid to gas, you could also just reduce the pressure. It's another fairly common way of doing that. And if you want to go the other direction, if you want to make some ice for your ice water, you just cool it down. Or if you want to take some steam and condense it, you cool it down. Alright, I think we'll go ahead and call it there for this video. So we'll jump into the intermolecular forces in earnest here in the next video. So I will see you there, and we'll talk about inter versus intramolecular forces.